In our previous lesson, we introduced you to queue data structure. We talked about queue as abstract data type, or ADT. As we know, when we talk about a data structure as abstract data type, we define it as a mathematical or logical model. We define only the features or operations available with the data structure and do not go into implementation details. In this lesson, we are going to discuss possible implementations of queue. I will do a quick recap of what we have discussed so far. A queue is a list or collection with this restriction, with this constraint that insertion can be performed at one end, that we call rear of queue or tail of queue, and deletion can be performed at other end, that we call the front of queue or the head of queue. An insertion in queue is called enqueue operation. A deletion is called dequeue operation. I have defined queue ADT with these four operations that I have written here. In an actual implementation, all these operations will be functions. Front operation should simply return the element at front of queue. It should not remove any element from the queue. Is empty should simply check whether queue is empty or not. And all these operations must take constant time. Enqueue, dequeue, or looking at the element at front, the time taken for any of these operations must not depend upon a variable like number of elements in queue, or in other words, time complexity of all these operations must be big O of 1. Okay, so let's get started. We are saying that a queue is a special kind of list in which elements can be inserted or removed one at a time, and insertion and removal happen at different ends of the queue. We can insert an element at one end and we can remove an element from the other end. Just the way we did it for stack, we can add these constraints or extra properties of queue to some implementation of a list and create a queue. There are two popular implementations of queue. We can have an array-based implementation and we can have linked list-based implementation. Let's first discuss array-based implementation. Let's say we want to create a queue of integers. What we can do is we can first create an array of integers. I have created an array of 10 integers here. I have named this array A. Now what I'm going to do is I'm going to use this array to store my queue. What I'm going to say is that at any point, some part of the array starting an index marked as front till an index marked as rear will be my queue. In this array, I'm showing front of the queue towards left and rear towards right. In earlier examples, I was showing front towards right and rear towards left. Doesn't really matter. Any side can be front and any side can be rear. It's just that an element must always be added from rear side and must always be removed from front. So if at any stage a segment of the array from an index marked as front till an index marked as rear is my queue, and rest of the positions in the array are free space that can be used to expand the queue, to insert an element to enqueue, we can increment rear. So we will add a new cell in the queue towards rear end, and in this cell we can write the new value. Element to be inserted can come to this position. I'll fill in some values here at these positions. So we have these integers in the queue, and let's say we want to insert number 5. To insert, we will increment rear. Of course, there should be an available cell in the right, an available empty cell in the right, and now we can write value 5 here. After insertion, new rear index is 7. And the value at index 7 is 5. Now dequeue means we must remove an element from front of the queue. In this example here, a dequeue operation should remove number 2 from the queue. To dequeue, we can simply increment front, because at any point only the cells starting front till rear are part of my queue. By incrementing front, I have discarded index 2 from the queue, and we do not care what value lies in a cell that is not part of the queue. When we will include a cell in the queue, we will overwrite the value in that cell anyway. So just incrementing front is good enough for dequeue operation. Let's quickly write pseudocode for whatever we have discussed so far. In my code, I will have two variables named front and rear, and initially I'll set them both as -1. Let's say for an empty queue, both front and rear will be -1. To check whether queue is empty or not, we can simply check the value of front and rear, and if they're both -1, we can say that queue is empty. I just wrote isEmpty function here. -1 is not a valid index. For an empty queue, there will be no front and rear. In our implementation, we are saying that we will represent empty state of queue by setting both front and rear as -1. Now let's write the enqueue function. Enqueue will take an integer x as argument. There will be a couple of conditions in enqueue. If rear is already equal to maximum index available in array A, we cannot insert or enqueue an element. In such scenario, we can return and exit. I would rather use a function named isFull to determine whether queue is full or not. If queue is already full, we can't do much. We should simply exit. Else, if queue is empty, we can add a cell to the queue. We can add cell at index 0 in the queue. And now we can set the value at index rear as x. In all other cases, we can first increment rear, and then we can fill in value x at index rear. I can get this statement a rear equal x outside these two conditional statements because it's common to them. So this is my enqueue function. In the example array that I'm showing here, let's enqueue some integers. I'll make calls to enqueue function and show you the simulation in the figure here. Let's say first I want to insert number 2 in the queue. I'm making a call to enqueue function passing number 2 as argument. The queue is empty, so we will set both front and rear as 0. Now we will come to this statement. We will write value 2 at index 0. So this is my queue after one enqueue operation. Front and rear of the queue is same. Let's make another call to enqueue. This time I want to insert number 5. This time queue is not empty, so rear will be incremented. We have added a cell to the queue by incrementing rear, and now we will write the value 5 at the new rear index. Let's enqueue one more number. I have enqueued 7. Let's now write dequeue operation. There will be a couple of cases in dequeue. If the queue is already empty, we cannot remove an element. In this case, we can simply print or throw an error and return or exit. There will be one more special case. If the queue has only one element, in this case, front and rear will not be -1, but they will both be equal, because we are already checking for -1 case in isEmpty function in the previous if. In this else if, we can simply check whether front is equal to rear or not. If this is the case, a dequeue will make the queue empty, and to mark the queue as empty, we need to set both front and rear as -1. This is what we had said, that we will represent an empty queue by marking both front and rear as -1. In default or normal scenario, we will simply increment front. We should really be careful about corner cases in any implementation. That's where most of the bugs come. Okay, so this finally is my dequeue function. In this example here, at this stage, let's say we want to perform a dequeue. Queue is not empty, and we do not have only one element in the queue. So we will simply increment front. Before incrementing, we could set the value in this cell at index 0 as something, but the value in a cell that is not part of queue anymore doesn't really matter. At this stage, it doesn't really matter what we have at index 0 or index 3 or any other index apart from the segment between front and rear. When we will add a cell in the queue, we will overwrite the value in that cell anyway. Let's now perform some more enqueues and dequeues. I'm enqueuing 3, and then I'm enqueuing 1. With each enqueue, we are incrementing rear. I just performed some more enqueue here. Now let's perform a dequeue. If I'll perform one more enqueue here, rear will be equal to maximum index available in the array. Let's enqueue one more. Now at this stage, we cannot enqueue an element anymore because we cannot increment rear. Enqueue operation will fail now. There are 2 unused cells right now, but with whatever logic we have written, we cannot use these two cells that are in the left of front. In fact, this is a real problem. As we will dequeue more and more, all the cells left of front index will never be used again. They will simply be wasted. Can we do something to use these cells? Well, we can use the concept of a circular array. Circular array is an idea that we use in a lot of scenarios. The idea is very simple. As we traverse an array, we can imagine that there is no end in the array. From 0 we can go to 1, from 1 we can go to 2, and finally when we will reach the last index in the array, like in this example when we are at index 9, the next index for me is index 0. We can imagine this array something like this. Remember, this is only a logical way of looking at the array. In circular interpretation of array, if I'm pointing to a position and my current position is I, then the next position or next index will not simply be I plus 1. It will be I plus 1 modulo the number of elements in array or the size of array. Let's say n is the number of elements in array. Then the next position will be I plus 1 modulo n. The modulo operation will get us the remainder upon dividing by n for any I other than n minus 1. This modulo operation will not have any effect, but for I equal n minus 1, next position will be n modulo n, which will be equal to 0. When you divide a number by itself, the remainder is 0. Previous position in circular interpretation of array will be I plus n minus 1 modulo n. We could simply say I minus 1 modulo n just to make sure this expression inside the parenthesis is always positive. I'm adding n here. Give this some thought. You should be able to get why it should be I plus n minus 1 modulo n. Now with this interpretation of array, we can increment rear in an NQ operation as long as there is any unused cell in the array. I'm going to modify functions in my pseudocode now. Is empty will remain the same. We are still saying that for an empty queue, front and rear will be minus 1. Let's scroll down and come to NQ. Now in circular interpretation, I will call my queue full when the position next to rear in circular interpretation, that we will calculate as rear plus 1 modulo n, will be equal to front. So we will have a situation like this. Right now the next position to rear in circular interpretation is front. So there is no unused cell. The complete array is exhausted. Nothing will change in this condition. If Q is empty, we can simply set front and rear as 0. In the last else condition, we will increment rear like this. We will say rear is equal to rear plus 1 modulo n, where n is number of elements in the array. With this much change, my NQ function is good. Now let's make a call to NQ and insert something in this array here. I want to insert number 15. We will come to this last else condition. Rear right now is 9, so this expression will be 9 plus 1 modulo n. N is 10 here. The size of this array A is 10 here. This will evaluate to 0. Now my new rear is 0. I will write number 15 here. Let's now see what we need to do in dequeue function. Nothing will change in the first two conditions. If queue is already empty, or if there is only one element in the queue, we will handle these cases in same manner. In the final else, when we are incrementing front, we need to increment it in a circular manner. So we will say front equal front plus 1 modulo n, where n is number of elements in the array, total number of elements in the array, or size of array. Now let's perform a dequeue. We will come to this condition. Front right now is 2, so this will be 2 plus 1 modulo 10. One more cell is available to us now. This much is the core of our implementation. Front operation will be really straightforward. We simply need to return the element at front index. Here also we first need to check whether queue is empty or not. We should return a front only when front is not equal to minus 1. All these operations, all these functions that I have written here will take constant time. Their time complexity will be big O of 1. We are performing simple arithmetic and assignments in the functions and not doing anything costly like running a loop. So time taken will not depend upon size of queue or some other variable. I'll leave this here. It should not be very difficult converting this pseudocode to a running program in a language of your choice. If you want to see my code, you can check the description of this video for a link. Thanks for watching.